Okay, so today we begin discussing some general constructions of locally convex spaces. That is, some general methods of building new spaces out of some initial data. And we start with quotients. So suppose we have a topological vector space X and vector subspace X0. Then we can form the quotient of X modulo X0, and we want to topologize the space. To topologize it, we denote by Q the quotient map from X to the quotient. And we define the standard quotient topology on the space as follows. The quotient topology on X modulo X0 is defined as follows. By definition, a subset U of the quotient is open. By definition, if its pre-image under Q is open in X. So this is the standard definition, which applies actually to any topological space and to any equivalence relation. But we are interested in this definition in a special case of topological vector spaces. Well, let's look at some basic properties of the quotient topology. Proposition. First of all, I claim that if we equip a quotient with this topology, then it becomes a topological vector space. This is a topological vector space. Second, the quotient map Q is continuous and open. Continuous and open. Property 3, if say beta is a base at 0 in X, then if we apply Q to any element from beta, to all elements of beta, Q of U, where U rounds over beta, this family will be a base at 0 in the quotient. Property 4, the quotient of X modulo X0 is Hausdorff, even only if X0 is closed in X. And finally, if X is locally convex, then so is the quotient. Well, the proof is an exercise for you. It is more or less straightforward. Actually, almost everything is almost immediate from the definition of the quotient topology. Maybe well, for example, 5 is immediate from 3, because, well, if beta consists of convex sets, then all sets of the form Q of U are also convex. Maybe the only point which is not entirely trivial is the right to left implication in Fourier. So to prove that if x0 is closed, then the quotient is Hausdorff. But this is not very hard. It's a useful exercise. Okay, so suppose that X is a locally convex space, and suppose we are given a defining family of seminorms on X. Can we explicitly construct a defining family of seminorms on the quotient? Well, the answer is yes. And the construction of such a family involves the notion of quotient seminorm. So let's call the following definition, the definition which you probably know from your functional analysis course. So we start with a vector space. X is a vector space. A vector subspace x0 of X. And suppose that P is a seminorm. P is a seminorm on X. We define the quotient seminorm, of P to be a function P hat defined on the quotient of X modulo x0. This is a non-negative function given by the following formula. If we take an element of the quotient in the following form, so little x is a representative of this element, and we take the infimum of P of X plus Y, where Y runs over x0. So this is the quotient seminorm of P. It's straightforward to show that P hat is indeed a seminorm. P hat is a seminorm. So this is the quotient seminorm, and it actually has a nice geometric meaning. Little observation. So let's denote by rho P the semi-metric generated by P. So this is just P of X minus 1. This is a semi-metric on X generated by P. Then P hat evaluated at X plus X0 is nothing but the infimum of the distances with respect to rho P between X and points in Y in X0. This is almost the definition of the quotient seminorm, but the only difference is that we replaced here a plus by minus. But of course, when if Y runs over X0, then minus Y also runs over X0, over X0. So this is our original definition. This is nothing but the distance with respect to this semi-metric between X and X0. So this is the geometric meaning of the quotient seminorm. Okay. So now we have the following simple result. Position. Suppose that X is a locally convex space where P is a defining family of seminorms on X, and we assume that P is directed. A directed defining family of seminorms. Then the quotient topology on X modulo X0, the quotient topology on the quotient is generated by the family of all quotient semi-norms P hat, where P runs over big P. The proof is needed from the following short formula, which is, well, formally this is an exercise, but it's a very easy exercise. If we take the open ball corresponding to any semi-norm P of radius epsilon and apply Q, what we get is, again, the ball corresponding to the quotient semi-norm P hat of the same radius epsilon. So this equality either follows from the definition of the quotient semi-norm. So this is a simple exercise. And if we now look at this formula, we see that this formula actually implies what we need. Because on the one hand, since P is directed, it's essential here, since P is directed, all such balls form a base at 0 in X. Not just a subbase, but a base. And we already know that after we apply Q to the base at 0, we get base at 0 in the quotient. So we see that such balls form a base of neighborhoods of 0 in the quotient. And this is precisely the base of the topology of the base of neighborhoods of 0 in the topology generated by this family. So the quotient topology and the topology generated by this family are identical. And that's it. Okay. The next result is almost trivial, but is very important. It is a so-called universal property of quotient. Universal property of quotients. It's basically the same as universal property of quotients in the context of normed spaces. So suppose that X is a topological vector space, X0 is a vector subspace of X. Then, for every topological vector space Y, and for every continuous linear map T from X to Y, such that T vanishes at X0. So every such map factors through the quotient. This is T. This is the quotient of X modulo X0, Q. So for every such T, there exists a unique continuous linear map T hat such that the diagram commutes. So every T that vanishes at X0 factorizes through the quotient. Well, actually it is almost nothing to prove here, because the existence and the uniqueness of such a linear map T hat, well, I'm assuming this is known from your linear algebra course. The only point which has to be proved here is the continuity of T hat. Well, to show that T hat is continuous, we just observe the following. We must show that the preimage of every open set is open. So this set has to be open at the quotient. And to prove that it is open at the quotient, we must prove that its preimage under Q is open in X, just by the definition of the quotient topology. But the commutativity of the diagram implies that this is nothing but the preimage of T, the preimage of U under T, which is open by the continuity of T. And that's it. Well, this result, the universal property of quotients, can equivalently be stated as follows. Theorem 1 prime, which is basically equivalent to theorem 1. So for every topological vector space Y, we may consider the following map, which acts from the space of all continuous linear operators from the quotient to Y to the space of those continuous linear operators from X to Y, which vanish at x0. And the map, this arrow, takes every S, where S acts from the quotient to Y, to S composed with Q. Well, clearly S composed with Q is a map from X to Y, and it vanishes at x0. So this arrow is well defined, and I claim that this map is bijective. This is just another form of theorem 1, because, well, theorem 1 basically says that whenever we take any map from here, there is a unique preimage in this space. This means exactly that this arrow is bijective. Okay. A useful extension of theorem 1, well, some a little more piece of information is theorem 2. So suppose that x, x0, y, t, and t hat. So suppose they are as in theorem 1. Then I claim that t hat is open, even only if t is open. And second, which is basically corollary of 1, t hat is a topological isomorphism, even only if t is open. And x0 is exactly the kernel of t. Okay, the proof is very easy, so it's an exercise for you. What is really important here is that this statement emphasizes the difference between algebra and linear algebra and functional analysis. So let me remark that in general, if T is a linear map from X to Y, then the quotient of X modulo the kernel T of T is not isomorphic to the set theoretic image of T, where T of X is put with the topology induced from Y. Well, why is it so? If we look at statement 2, we see that this isomorphism holds even only if T is an open map onto its range. This formula holds. This is true if and only if T is an open map from X onto T of X. And in general, this property fails, and so we have no isomorphism between the quotient modulo the kernel and the set theoretic image. As a result, this remark shows that the category of topological vector spaces is not abelian. And in fact, it's typical for functional analysis. Most interesting categories of functional analysis are not abelian. On the other hand, we'll see now that a remorphism in the category of topological vector spaces has a kernel and a co-kernel. So let's discuss kernels and co-kernels. Well, to begin with, let's call a general category theoretic definition. Suppose that A is a category with 0. So let's recall that an object of a category is a 0 object if it is both an initial object and a terminal object. So there is a unique, for every x, for every object x, so there is unique morphism from x to 0 and unique morphism from 0 to x, which is called the 0 morphism. And suppose that phi is a morphism in our category, phi from x to y is a morphism A. Then, by definition, the kernel of phi is a pair consisting of an object big K. K is an object, and little k is a morphism from big K to X, such that this pair satisfies the following conditions. Let me draw a picture. So this is phi, this is K, this is little k. So first of all, the composition of these two arrows is 0. Phi composed with K is 0. And second, once we have an object Z and a morphism from Z to X, so psi, such that this composition is 0 for every Z and for every psi from Z to X, such that 5 psi is 0. There is a unique morphism from Z to K, as denoted by chi. There is a unique chi from Z to K, such that the diagram commutes. Okay, so this is a general category theoretic definition of the kernel of a morphism in a category with 0. Here is a basic example. Actually, some basic examples. Suppose that A is any of the following categories. We may take the category of abelian groups, or the category of vector spaces, or, for example, the category of sets with a base point. So set star is category of sets with a base point. That is, the objects are pairs consisting of a set and a distinguished base point of the set. And the morphisms are maps between such sets, which preserve the base points. It is a category with a 0 object. The 0 object is the set consisting of a single point. So if A is any of these categories, then every morphism has a kernel. Every phi has a kernel. And more exactly, the kernel of phi is just the preimage of 0. And I forgot to introduce the respective notation. Let me do it here. Notation. The object big K is denoted like this, and the morphism little k is denoted like this. The kernel phi is just the preimage of 0, and little k is just the inclusion map. It's a simple exercise to show that this is indeed the kernel in the category theoretic sense. An equivalent but useful definition of a kernel looks like this. The kernel of the morphism phi in our category A is an object K, or just denoted by the kernel of phi, together with the natural isomorphism. Of the following form, morphisms from Z, say, to the kernel are in one-to-one correspondence with the kernel of the following map induced by phi. So it acts from this set to this set. So now this arrow is induced by phi in the usual way. So it takes every morphism from Z to X with its composition with phi. Both home sets are actually equipped with base points. The base point here and here is the 0 morphism. And the kernel is, the kernel is just the preimage of 0. The useful exercise is to show that these definitions are equivalent. In fact, this is our general principle of category theory. Quite often, to define some, to give a definition of some general construction in a more or less arbitrary category, we first construct this explicitly in a category of sets, or in category of sets with a base point, and then expand this definition to an arbitrary category by using suitable home functors. So this principle is very common, and we'll meet it several times in our course. Okay, so now if we now look at the category of topological vector spaces, we easily get to the following result. This is also an exercise for you. If A is the category of topological vector spaces, then every morphism in the category of topological vector spaces, let's denote this category like this. Every morphism phi has a kernel and this kernel is nothing but the preimage of 0 equipped with the subspace topology. That is the topology induced from X. And the respective morphism is just the inclusion map. In fact, the same result holds for many concrete subcategories of the category of topological vector spaces. The same holds for example, for the following full subcategories. Of the category of topological vector spaces. We can take, for example, the category of Hausdorff, locally of Hausdorff topological vector spaces, as denoted by HTVS. Hausdorff topological vector spaces, or the category of locally convex spaces, LCS, locally convex spaces. Or we can take a category of Hausdorff locally complex spaces. In all such cases, every morphism has a kernel, and the kernel is the same as the kernel is the category of topological vector spaces. This is the preimage of 0 equipped with a subspace topology. Okay, let's now discuss co-kernels in our category. Again, we start with the general category theoretic definition. Suppose that A is again a category with 0 object. And phi is a morphism. Okay. Then the co-kernel of phi is a pair, big C and little c, where big C is an object, our category, and little c is a morphism from Y to big C, such that this pair, big C and little c, is the kernel of phi in the opposite category. Kernel of phi in the opposite category. The opposite category of A has the same objects, and morphisms in the opposite category are the morphisms from X to Y in the opposite category are by definition the morphisms from Y to X in the category A. So we just formally reverse all the arrows, and we get the definition of a co-kernel. A useful exercise is to give an explicit definition in the spirit of this one. Just reverse the arrows and get the definition of the co-kernel. And the equivalent definition looks as follows. Well, first of all, some notation. The object big C is denoted like this, and the morphism little c is denoted like this. And an equivalent definition in the spirit of this one looks as follows. Definition prime. The co-kernel of phi is an object of our category together with the following natural isomorphism. So the morphisms from C to Z, to an arbitrary object Z, are in a one-to-one correspondence with the kernel of the following map from Y to Z to from X to Z. Well, again, this arrow is given by composing with phi on the right. That is, if we have a morphism from Y to Z and compose it on the right with phi, we get a morphism from X to Z. So this arrow is well defined. And this arrow is a morphism in the category of sets with a base point. The base points here are the zero morphisms. So the kernel of this map is nothing but the set of all morphisms from the co-kernel of phi to Z. So we see that the co-kernel of phi in an arbitrary category with 0 can be defined in terms of kernels in the category of sets with a base point. Okay, again, useful exercise it is to prove the equivalence of the two definitions. And here are some examples and exercises at the same time. If take the category of abelian groups, or the category of vector spaces, then every morphism has a co-kernel. More exactly, the co-kernel of phi is nothing but the quotient of y modulo the range of phi, and the respective morphism is just the quotient map. You can now take the category of topological vector spaces, or the category of locally convex spaces. And again, every morphism has a kernel. Every morphism has a co-kernel. And again, this is the quotient, equipped with the quotient topology. And finally, if you take the respective categories of Hausdorff spaces, if A is either the category of Hausdorff topological vector spaces or the category of Hausdorff locally convex spaces, then again, every morphism has a co-kernel. But now, the situation is a little bit different. So let's recall that in general, the quotient is not Hausdorff. And to get a Hausdorff quotient, we must quotient out a closed subspace. But phi of x is not necessarily closed. It turns out that if we quotient out the closure of phi of x, then what we get is precisely the category theoretic co-kernel. So we see that in the Hausdorff categories, every morphism still has a co-kernel, but it is different from the co-kernel in the category of all topological vector spaces, or all that is not necessarily Hausdorff locally convex spaces. Okay. Now, before we proceed with other constructions, let's discuss two general methods of topologizing vector spaces. So let's discuss the so-called projective and inductive locally convex topologies. Okay, let's start with the projective locally convex topology. Suppose we have a vector space, X. This is the space we want to topologize. And suppose we have a family, Xi, a family of locally convex spaces. A family of locally convex spaces. And suppose we have a family of linear maps, phi I, from X to Xi. A family of linear maps. We can now topologize X as follows. By definition, the projective locally convex topology of X generated by the family phi I is defined to be the locally convex topology, is the locally convex topology of X generated by the following family of seminorms, was denoted by P proj. It consists of all seminorms of the following form. P composed with phi I, where I runs over our index set big I, and for every I, P runs over the family of all continuous seminorms on Xi. So by definition, this is the defining family of seminorms for the projective locally convex topology on X. Well, let's look at some simple basic properties of this topology, proposition. First of all, I claim that we can replace here the family of all continuous seminorms on Xi by an arbitrary defining family of seminorms. And we still get the same topology on X. So we can replace the family of all continuous seminorms in the above formula, as noted by star, by any defining family of seminorms. Any defining family of seminorms on Xi. And we get the same topology on X. Second, the projective locally convex topology on X is the weakest locally convex topology on X, making all the maps phi I continuous. Property 3 is similar to property 2, but now I claim that this topology is the weakest among all topologies on X, making all these maps continuous.
Not necessarily vector topology.
No, the weakest in the class of all topologies.
It means projective is equal to initial.
Yeah, exactly. So this is just the initial topology which you know from your general topology course. Property 4. Property 4. This topology, the projective locally convex topology, is uniquely characterized by the following property. This is the only locally convex topology on X with the following property. If we have a locally convex space, say Y is a locally convex space, and phi is a linear map from Y to X. Linear map. Then phi is continuous. Even only if phi composed with every phi I is continuous for every I. So this is a picture of the situation. This is phi I. So a map from Y to X is continuous if all such compositions are continuous. Property 5 is about basis of neighborhoods of 0. If, say, sigma I is subbase at 0 in Xi for every I in our index set, then the following family, the family which consists of all pre-images of sets from sigma I. Here, little I runs over our index set, and for every I, U runs over sigma I. So the family is a subbase at 0 in X. where X is equipped with the projective locally convex topology. I'd like to stress that if we consider, even if every sigma I is a base of neighborhoods of 0, this family is still a subbase. Normally it is not a base. To get a base, we must add finite intersections. Sometimes it will be a base, but this will be discussed a bit later. Okay. Again, the proof is a more or less straightforward exercise. The only point which is not entirely straightforward is statement 3. Because here we consider all topologies, not necessarily locally convex. But nevertheless, it's not very hard to prove that this is indeed true. And parts 1, 2, 4, and 5 are almost immediate from the definition. Let's look at some examples of projective locally convex topologies. Example 1 is more or less degenerate, namely the weakest locally convex topology. The weakest locally convex topology, which is the same as the anti-discrete topology. X is the same as the projective locally convex topology generated by the only map from X to 0. Well, this is more or less clear from the definition, because the defining family of seminorms in this case consists of the single seminorm which is identically 0. So it generates the weakest, that is anti-discrete locally convex topology. Example 2. If X is any topological vector space, any locally convex space, any locally convex space, and X0 is a subspace, a vector subspace, then the topology on X0 induced from X is nothing but the projective locally convex topology generated by the inclusion map of X0 into X. Example 3. So let's start with an arbitrary topological vector space X. And let's consider the weak topology. The weak topology for X, which was defined at the first lecture. So it's defined by a family of seminorms indexed by continuous linear functionals on X. And it's easily seen from the definition that this topology is nothing but the projective locally convex topology generated by the family of all continuous linear functions, where f runs over the dual space X prime. Well, before we discuss example 4, let's introduce some general notation. Suppose that we have suppose real P is a seminorm on an arbitrary vector space on a vector space X. Now let's observe that the preimage of 0 is always a vector subspace of X. This is immediate from the triangle inequality. So we will take the quotient of X modulo this subspace, and let's denote it by XP. we make xp into a normed space. xp is a normed space. With respect to the quotient norm, p hat of p. So p is a semi-norm on x. So we quotient out the zero subspace of p. We take the quotient semi-norm on xp, and this quotient semi-norm is actually a norm. And moreover, this norm is given by the following simple formula. It is just p of x. So we take any representative of the respective class and calculate its semi-norm. Well, and formally this is a little exercise, but it is actually very easy. So this is a very useful construction. So it produces a norm space out of a semi-norm on an arbitrary vector space. Now, example 4. Example 4. Actually, this is a very general example because it is about an arbitrary locally convex space. So suppose that X is an arbitrary locally convex space, and P is the defining family of seminorms on X. I claim that the topology generated by P is nothing but the projective locally convex topology generated by the family of the following maps, as denoted by pi p, from X to XP, where little p runs over big P, and pi p is, well, from the viewpoint of linear algebra, pi p is the respective quotient map. But it is not a good idea to look at pi p as a quotient map, because the topologies are different. So the topology on XP is not the quotient topology on X. The topology on XP is the topology of a norm space given by this unique, this explicit, this concrete norm. So from the topological point of view, pi p is not quotient map. It's just, well, a map from X to the norm space XP given by this formula. Well, if you look at this statement, it's just, this statement is trivial. If we recall the definition of tau of P, so the subbase is formed by all the family of all open balls, but these open balls are nothing but the preimages of the open balls in XP over all P, and so we get the definition of projective topology. So this is trivial, but this is very useful. The usefulness of this example will be clear when we discuss, for example, completions of locally convex spaces.
So the point of this statement is that if we can prove something from normed spaces and commutes with projective limits, we can prove that it's true for TVS, right?
Yeah, sometimes. Not always, but this trick works in many concrete situations. So sometimes this observation makes it possible to reduce some statements about topological vector spaces, about locally convex spaces, to the case of norm spaces. This doesn't. I don't claim that this trick works in all situations, but there are some important situations where it works. So in other words, we see that any locally convex topology is the projective locally convex topology generated by a family of maps with various norm spaces. And in fact, moreover, we can replace here, moreover, we can replace XP by any norm space containing XP, by any norm space YP containing XP. Here's a concrete special case of this situation. Special case. Suppose that X is a topological space. And for every compact subset K of X, we can consider the restriction map Rk from C of X to C of K. Restriction map. So now every C of K is a Banach space, of course. C of K is a Banach space. With respect to the subnorm. And applying this example 4, we see that the topology of compact convergence, the topology of compact convergence on C of X is nothing but the projective local convex topology generated by the family of all such restriction maps. So here, K runs over the family of all compact subsets of X. Well, I don't claim here that a C of K is the quotient of C of X with respect to the zero set of the respective second order. In general, the respective XP space consists of those continuous functions of K, which can be continuously extended to X. So if X is nice enough, if it is Tikhonov space, then Rk will be surjective. But in general case, it is not surjective, but this is not very essential because of this remark. So we simply replace the respective quotient by the bigger space consisting of all continuous functions on K.
Actually, wait. If this normal topology is not the quotient topology, then if we have two norms, two semi-norms on X, one of which dominates the other, we do not in general have a morphism between the corresponding norm spaces.
Well, we have a map between the corresponding norm spaces, yes.
Do we have it or not?
Well,
Continuous, I mean.
Yeah, well, if we have two, say norms, say P and Q, yeah, so we have a map from here to here, and if Q dominates P, then we have a map from here to here. That's true.
Continuous.
Continuous, yeah.
In these topologies.
If yeah, for in the norm topologies, yes.
Right.
But in general, it is not an isomorphism. Of course, Q may be stronger than P, and this observation will be useful when we discuss completions. In fact, in many cases, completions can be reduced to projective limits, which is quite useful. Okay. Let's now look at inductive local convex topologies. We start with a vector space, X, vector space, a family of locally convex spaces Xi, a family of locally convex spaces, and a family of linear maps phi I from Xi to X. A family of linear maps. So we wanted to topologize X. So when we discussed projective local convex topologies, the initial data was different. So we had a family of maps from X to Xi. And now we have a family of maps from Xi to X, that is in the opposite direction. By definition, the inductive the inductive locally convex topology on X generated by the family phi I is the locally convex topology generated by the following family of seminorms. That's denoted by P ind, and it consists of those seminorms P on X. P is a seminorm on X, such that P composed with phi I, this is a seminorm on Xi, is continuous for every I. Okay, at this point, let me stress the difference between the definition of the inductive locally convex topology and the definition of the projective locally convex topology. Oh, it's, where is it? So here, when we define the projective locally convex topology, we see that this family of seminorms is quite explicit. So when we start with an arbitrary defining family of seminorms on every xi, we simply compose these seminorms with phi I, and we get a very concrete family of seminorms on X. Here, the situation is quite different. Here, the respective seminorms are described by a certain property. So all such seminorms have to be continuous. But there is no explicit construction of all such seminorms P. We only describe a certain property which has to be satisfied, but we don't have any explicit construction of such seminorms P. This phenomenon is a source of many problems in the theory of inductive locally convex topologies. Sometimes we may replace this family of seminorms by a more explicit one, and we'll discuss some such examples a bit later. But in general case, we have only this very abstract definition of the defining family of seminorms. Okay, let's now look at some general properties of the inductive locally convex topology, a proposition. First of all, this topology is the strongest locally convex topology on X, making all the maps phi I continuous. This is more or less immediate from the definition. But if you now compare this situation with the projective locally convex topology, we see an essential difference. I don't claim that this is the strongest in the class of all topologies.
It's trivially fails when we put all zeros.
Yeah. And what is much more interesting, if we, what is more interesting is that I cannot replace here locally convex topologies by vector space topologies. This is not trivial, but this is true. Some details will be given in the next exercise sheet. But there are some examples showing that if we consider the strongest vector space topology, making all the maps phi I continuous, then in general it will be stronger, strictly stronger than the inductive locally convex topology. Property 2 is more or less dual to the respective property of the projective locally convex topology. Namely, the inductive locally convex topology is the only locally convex topology on X. With the following property. if Y is a locally convex space, then if Y is a locally convex space, and if we have a linear map phi from X to Y, then this map phi is continuous. Even only if all such compositions phi I are continuous. Phi I is continuous for every I. So the picture looks as follows. This is phi, and this is phi I. So phi is continuous if and only if all such compositions are continuous. And property 3 describes a base of neighborhoods of 0 in X. So the following family is a base at 0 in our space. So it consists of those subsets U of X such that U is absolutely convex, absorbing, and such that phi, the preimage of U under E of every phi I is a neighborhood of 0. For every little I. Again, we see that this definition is very inexplicit. So we describe a certain property of such sets U, but we don't give an explicit construction. So this is similar to the spirit of the original definition of our topology. This is not very explicit, and as a result, the description of perspective base at 0 is not explicit. We just single out a property which has to be satisfied by such neighborhoods. Okay, let's now look at some examples of inductive locally convex topologies. Example 1. The strongest locally convex topology, which was discussed some time ago, is nothing but the inductive locally convex topology generated by the only map from 0 to X. Well, indeed, if we look at the definition of the inductive locally convex topology, we see that in this case, the defining family of seminorms consists of all seminorms, of all possible seminorms on X. And this family generates the strongest locally convex topology. Example 2. Example exercise 2 is about the quotient topology. Is X is a locally convex space, and X0 is a vector subspace. Then the quotient topology on the quotient X modulo X0 is identical to the inductive locally convex topology generated by the quotient map. In this special case, let's recall that in this special case, we have an explicit family of seminorms on the quotient. But this is actually a very special case of the inductive locally convex topology. Example 3 describes the canonical locally convex topology on the space of continuous compactly supported functions on an arbitrary topological space. So suppose X is a topological space, and let's denote by C sub C of X, the space of continuous compactly supported functions of X. The canonical locally convex topology of the space is defined as follows. We take an arbitrary compact subset K of X, and we denote by Ck of X the space of those continuous functions on X such that the support of F is contained in K. And we equip the space, we equip Ck of X with the supreme norm. So it is a norm space, and by the way, it's easy to show that it's a bound space. By definition, the canonical topology on the space of continuous compactly supported functions on X is the inductive locally convex topology generated by the family of all inclusion maps Ck of X into our big space C of X over all compact subsets K of X. So every Ck of X is a norm space. We consider all such inclusion maps, and this family of inclusion maps generates a topology on Cc of X. It is very important to distinguish between this canonical topology on Cc of X and the compact open topology induced from C of X. At the first glance, one may conjecture that these topologies are identical. But this is not the case. Useful exercise. Suppose that X is good enough. So suppose that X is locally compact, sigma compact, which means that it is a union of countable many compact sets, but non-compact. There are many such spaces. For example, the real line, or any open subset of Rn, or any topological manifold, and so on. Prove that Cc of X is not metrizable. So let's recall that C of X is metrizable. This was discussed at the end of the previous lecture. So one implies that the canonical topology on Cc of X is strictly stronger than the topology induced from C of X. Okay, example 4 is similar to example 2. But now we consider smooth compactly supported functions. So we start with an open subset U of Rn, and we denote by C of U, the space C infinity C of U, the space of those smooth functions on U which are compactly supported. The support of F is compact. The canonical topology on the space is defined as follows. Again, take any compact subset K of U, and we consider the subspace C infinity K of U, consisting of those smooth functions on U, whose support is contained in K. Next, we topologize this space, C infinity K of U. We equip it with the topology induced from C infinity of U. C infinity K of U with the topology induced from C infinity of U in the space of all smooth functions on U. Now the canonical topology on the space of smooth compactly supported functions C infinity C of U is by definition the inductive local economics topology. Generated by the family of the respective inclusion maps from C infinity K of U into C infinity C of U, where K runs over the family of co-compact subsets of U. Again, the situation here is similar with the space of continuous compactly supported functions. Since the topology on C infinity K of U is the topology induced from C infinity of U, one might conjecture that the same is true for all space of continuous compactly supported, of all smooth compactly supported functions. But this is not the case. Again, the useful exercise is to show that the canonical topology on the space is not metrizable. And this implies that this topology is strictly stronger. This topology is strictly stronger than the topology induced from C infinity of U. Oh, it's time to finish. So the last example, well, the details will be given in the exercise sheet. Example 5. It is the space of K consisting of germs of holomorphic functions. On a compact subset of Cn. So K is a compact subset of Cn, and O of K consists of germs of holomorphic functions. The canonical topology on the space is again the inductive local convex topology. Inductive locally convex topology generated by the family of all restriction maps from O of U to O of K, restriction maps, where U runs over the family of all open neighborhoods of K. So some details about this example will be given in the next exercise sheet. In particular, even in the case where K consists of a single point, so we have the space of germs of homomorphic functions at a single point, the space is not metrizable. This is also useful exercise. Okay, so that's all for today. At the next lecture, we discuss, we'll continue, we will proceed with other constructions of local complex spaces, and we discuss products, co-products, or which are the same as local complex direct sums, and more generally limits and co-limits. And well, the lecture will be similar to today's lecture. That is, all results will be almost trivial, but there will be many definitions and many concrete examples of topological vector spaces which can be obtained as projective limits, inductive limits, products, co-products, and so on.